I wanted to see if there was an option for a multiband end-fed half-wave for my particular scenario, which is a wooden post of approximately 5.48 metres and a tree at the far end of the garden. Currently it holds a fan dipole for 40 and 20 metres, so I have approximately 70 feet. So I did a bit of research on the internet, and I actually found that there was a commercial product out there already, and it has what I'm assuming to be a 49:1 balun or impedance transformer, and this particular antenna that I saw, it seemed to have it be like inverted L, sorry, not the inverted L format. This particular antenna that I saw was fed with a balun of whatever, it didn't specify, and it had one long arm for say 40 metres, and then it had shorter wires dropping down, which you trim back to get resonance on 20 and 17, for example. Then it looked like that they were in parallel, so the wires ran in parallel and then dropped down, so say if it was a 4-band, all 4 wires went back to the feed point on the balun. So to try and understand this, I wanted to model it in EZNEC, or EZNEC for the Americans. So during this video, on the long stretches when the EZNEC software is calculating the SWRs, I've skipped, chopped a chunk out of the middle to save the video being extremely long. So what this isn't is a tutorial on EZNEC, and nor is it a full planned multiband end-fed half-wave, so if you're expecting that, now's the time to quit out, and thank you. So let's crack on. So first of all, up in this area here, you can see roughly the path I followed, and as we step through I'll explain why we followed that sequence. So first of all, I wanted to just do a single band inverted L end-fed half-wave. The feed point, or the balun, is about 5 centimeters above ground, and my particular scenario, I've got 2 10-foot ground stakes within a few feet of each other, obviously in the ground, and then above that I have a wooden mast that's 5.48 meters roughly, and then my wire stretches across to a tree. Okay, so here's my original test. Here's roughly what the antenna would look like. If you're not familiar with EZNEC, you can equate this to north and south. Let's rotate it around like that. You can equate that to the north direction, that's the south direction, that's west, that's east, and that is height. So it's quite easy to use. If we zoom in there, let's see what we're actually doing. So in my first set of calculations, I placed at where it says number 2 here, this is the source, so this is where the balun is, and then there's a short patch down to ground. To see what the dimensions actually are, we can look here in this wires window. So this simply plots the end points of the wires and how they connect with each other. So you can see wire 1, that's the bottom one in the antenna image, is ground, and it shows its ground there, and it's nearly a metre high, so 0.9 metres up. That's roughly to where the bottom of my wooden pole is, attached to the side of a shed, and up she goes. And it's constructed of 1mm wire, and each wire has 20 segments. The segments is just, if you like, the resolution. So the more segments you have on a wire here, the more detail, or the more accurate you'll get the result out of the software. So that's roughly how it goes. So here we can see we've got 4 wires. If we click reset here, so there you can see how it is. So basically what I'm saying is we have the vertical upper wooden mast through a little loop, and then across to a tree here in this area here. So inverted L, if you like. What does that look like? Here's the bit that I'm going to chop out for you in a moment. To speed the calculation up, I use, say, 0.2 here as steps, but once I've ascertained a rough plot, then I will, if I want to go into more detail, I will reduce that step size for a much smoother curve on the image. So I'll show you. And remember, this is the bit that's going to chop out and suddenly jump to 30 megs. So on this SWR plot, the first thing we do here is change. This is showing us a 50 ohm impedance, so like fed straight with coax. This is showing us what it would be through a 49:1. And we can just literally scroll along and see that there's a resonance point there, not very good SWR, 7.2 megs. Here we have a harmonic, 14.8 roughly, 22 megs. So it's actually even just the end fed on 7 megs. If you get the length of the wire correct, you could probably tune it onto 14 megs and 21 megs. So you'll notice the bottoms of these look quite kind of notchy. If I increase the resolution, you'll see a much smaller curve. And when I calculate my antennas, I'm looking for a 2:1 plot. In fact, let's do it with this one here. So what frequency? 14.6. So we'll redo the SWR there, and then I'll explain what I'm looking for. So say 14.4 through to 15 megs, 0.0. So this is going to give us a higher resolution, and you'll see a smoother curve. Okay, so when you see it like this, you can say very definitely that the resonant frequency is going to be there, which says 14.71. I'm looking at this area for the info. I like to measure my antennas with two things: a 2:1 bandwidth, which is basically there, 14.48 through to approximately there, 14.93. That's the 2:1 bandwidth. This one doesn't go low enough, but I also calculate when that curve goes below 1.5:1, the 1.5:1 bandwidth as well. So I would create a small table there with 2-to-1 low frequency and high frequency, 1.5-to-1 low frequency and high frequency, and also what I deem to be the dead centre of the lowest point there as the resonant frequency. That's quite interesting data to look at later on. So we can see with this one it's 14.71, which is a little bit high. So if we were to, assuming it was can we put this to bring the frequency down a little bit, 14.7 down, we would extend the length of the wire slightly. It's not strictly true in this case because this is a harmonic that we're looking at, but that's typically what you would do. Say if you had a dipole, etc. Anyway, I followed this process through each of the bands, changing the lengths of the wires. Basically, the length of wire number 4. Everything else remained the same. Because obviously the height of the pole is the same, we just shorten this. So I did that for 14 megs and 18 megs and got a similar curve. So we achieved, shall we say, resonance at the right point for those three things. Then I hit a point about the fact that I actually wanted to. Then I hit upon the fact that the source was a metre off the ground, and I wanted to put it right down by the ground rods that I have. So we redid the design of this, if you like, for a take 2. So there it is zoomed in. Can we put wires on there? Wires, yeah. So we made the vertical wire, instead of a short piece and long piece, just one long piece, and we placed the source at the first segment of it. So the source we declare in here. So we say the source. Let's move this slightly. The source we've placed inside wire 1, 0% from end 1, so from this end here, which is ground, and it told us that it's placed it actually at 2.5, and that's because of the size of the segments. So 2.5% in, but that's good because it's basically close to the ground. And we'll just do a quick plot again. So what I actually found here was that for the 40 metre element, the SWR wasn't going low enough by a long shot, but for sure it's the same way that they calculate the end-fed half wave. Whether that's because it's the wrong combination of vertical versus horizontal, maybe just at my property, I don't know. But you can see 14.2 is down there, and again 21.4, and I think it's 28 megs is the other one. Yeah. So just on that 40 metre calculated one, it seems to work 14, 21, 28, not really down on 7 megs 40 metres, so that would be quite useful as it is. So yeah, we went through each stage like that, calculating again for 14 and 18 megs, and then I come up with and then what I like to do is to understand. So I sketch out in a notepad normally what my antenna is going to be and what the numbers of the wires are, and I find that for me is much easier. Let's see if we can get this on the screen too. Not quite. Okay, but basically this window here where you have the wire numbers 1 and 2, I find it much easier to populate that if I'm referring back to a drawing like this. So quite clearly I have the numbers on. So on the commercial antenna that I saw, and I really wish I could remember the manufacturer design or whatever, it seemed to suggest that they ran say in this case 3 wires in parallel up here, 3 wires parallel here, and then they dropped one down, say for 17 meters. 2 of them continued on, 1 drops down for 20 meters, and the remaining one is the 40 meter leg. And what they do here to tune it is I think they first of all tune the 40 meter leg to get the lowest SWR, and then these wires, which are literally just hanging down, they just trim them up, and they're deliberately made longer than they're supposed to be, so that when you find the resonant frequency using an analyzer or whatever, you can calculate how much you need to take off reasonably accurately. But they do it in stages, so they, for example, they would do 40, 20, then 17 trimming, and that's how they go. But I do believe that the version that I saw was fed at this point here, it didn't have the vertical part of it, but then feeding at that point there, you don't have a ground available right next to it. Yeah, so it can, or it is and does become a deep subject with whether you're going to have a short radial hanging off of here or nothing at all. And if in the coax that you would put some kind of choke there, being, say 6 turns in the coax or something like that. So that was our Visio idea, and after modelling it to that picture, we entered the data in there, and when we went to calculate it, this happened. Now the reason this has happened is because it doesn't like you putting or hanging those wires down. The wires that we hang down to trim, I placed midway along the length of the horizontal wire. It doesn't like that, so I had to do a retake, which we've called whoops. Again, I just knocked this up in Visio, did a retake there, and instead of having one long wire along here, I broke it down to smaller wires, and defined which was what for the tuning afterwards. So now wire 6 here is at the intersection of 2 and 3. So what we can say when we're actually putting it in the wires part of EZNEC, that we say wire 3 end 1 is where one end of 6 connects to, and wire 3 end 2 is where one end of 5 connects to. Or if we don't want to say that, we can say Y4 end 1 is where that connects. But that's basically how we worked it out. Let's close that out again. So we reworked it. The antenna now looks like this. same as in the Visio there. And we run the SWR on here too. And here's where it goes a bit messy. Welcome back. Alright, so again, get the right impedance. This is what we end up with. Roughly 7 megahertz with not a very good SWR. 13.8, so it's shifted E14 megs down a bit. 21 megs and 28.2. So it gets a little bit finicky trying to tune this, trying to trim this. So what I then did, just for curiosity, is I worked it, reworked it as a fan dipole, but only from from this point onwards. So it's one single wire up and then two out here. See if we can see that any better. Yeah, there we go. So one single wire up, then it splits at this point onwards. So let's check the SWR for that. So you can see it's pretty nasty. Even there we go. It's all over the place, and really the only area where it dips down here is about 17.8 megs. So really doesn't look that clever for an installation at this site. Whether that's to do with the vertical component here of wire 1, I don't know. But that's the way she goes there. So what's next? 2 parallel wires. Okay, so I took a slight redesign, and I'm thinking back to the antenna that was commercially available. Let's cancel that, that's not what I want to do. To view the antenna. So the one that was commercially available had parallel wires, albeit I believe from this point just going out in a line as opposed to the inverted L formation. But just here's actually what I mean. Let's zoom it right in there. Okay, so there we are. And the wires, just so that we can see what we're actually doing. So this shows that right down at the ground point where my ground stakes are, there's a short piece of wire 5 centimeters long. That's number 1. And because EZNEC likes to have those very defined points, the beginning of end of the wire where you connect, at the beginning of wire number 2, so this area here is my vertical 5.48 meters for the 40 element, and then it goes out about 15 meters to the right, and my 17 meter, my 18 meg is this point of wire number 3, goes vertical, stops a few centimeters short of the other wire and runs out parallel. So if we reset that, you can see they both run up and out. Let's check out the SWR for that. Yep, so let's get the right impedance. Again, not really too much in terms of efficiency from the SWR, except perhaps here 14 megs and here 20.2 megs, which is not in a band. So you can see again some trimming required, not very useful at this site. Okay, so one of the things I wanted to show was the far field plots. I was kind of expecting that they were going to fire similar to a dipole, a lot of energy at right angles to the wire, but in actual fact, let's scrap. Let's change this plot type. I want 3D, three-dimensional. There we go. Anyway, I will complete my sentence. In actual fact, it's reasonably omnidirectional. So this is looking from above. If you're a bird flying over the top, about to no, if you're a bird flying over the top, that's what you'd see. Now that's not too far off of omnidirectional. Remember, the wire is running in this along this y-axis. So there is a little bit more left and right, but there's also a fair amount going north and south as opposed to the east and west, right? So let's bring that down, have a look. Not entirely a cloud burner either, it comes out reasonably low here. So we can check out the, let's change it to 2D, that's the better way of viewing it. Elevation, there we go. So you can see down towards the bottom there. Is it not going to let me do this? There we go. It comes up, I'll just show you with the mouse, it comes out reasonably low before it climbs up, as opposed to being, say, more like a tennis ball pattern above it. So it does, it will perform reasonably well as opposed to cloud burn. That's probably as far as we want to go with the explanation in that. But yeah, very useful ways of looking at that. I don't know if you can see inside the top here. I think we can change where that dot's displayed, and it will feed back the information down on the lower image as well. You see the info changing here. Yeah, so what's my conclusions on all of this really? For a single band end-fed half wave, the SWR curves are reasonably nice and they're manageable. For the multi-band ones, they get very notchy and hard to manage entering, basically because of the interactions between them. So for this site, I currently have a fan dipole up, which has got a perfect SWR right away across 40 and 20 meters, and we'll tune on all other bands as well with an auto tuner. The end-fed half-wave multiband is not one I'm going to bother experimenting with. That's it. So thanks for taking the time if you've made it this far. In super summary, not for me.
So this video, if you like it, our video, comment down below a thumbs up.
Thanks for watching VA3SII. Bye.